Okay, so we have a new question in front of you. Go through the question. Which of the following molecule is chiral? Okay, so we have isobutane, neopentane, secondary butyl chloride, all. So how will you check this? So you should be able to know how to draw the structure of this compound. Isobutane means first we need to draw CH3, CH, CH3. This indicates iso, correct? So butane, only 3 carbon atoms are there. So we will draw one more, isobutane. So this is basically isobutane. Now if you see here 1, 2, 3, 4, 4 carbon atoms is there. Okay, and this indicates isoposition. This indicates isoposition. Clear? Now if you see here whether this compound is chiral or not, please check. No. Why? Because if I am going to draw this like this, you can understand here for this valence, this is same as this one and this is same as this one. We know that for a carbon to be chiral, its 4 valencies should be the different. Then only we can say that is chiral. Correct? So isobutane is not chiral. Next we will check neopentane. So how will you write neopentane? So neopentane means you have CH3, okay, then CH3, CH3 and CH3. This is called neopentane. Now if you look at neopentane, surely we know that all the 4 valencies are same actually. So but as per this carbon to be chiral, its 4 valencies should be different. So I am sure this neopentane is also not chiral. So next we will try out the other one, the last one, that is secondary butyl chloride. Secondary butyl chloride. So we can draw that CH3, okay, CH3, CH, okay, CH3, CH, CH2, Cl. Okay, this is normal butyl chloride. Now they are saying secondary butyl chloride means we need to draw this chlorine at the secondary position. So we can say that will be either here or here. So I can write the chlorine here. So this is called secondary butyl chloride. So 1, 2, 3, 4. So but, 1H is replaced, so it will become butyl at the second position. So secondary butyl chloride, because it is connected to 2 other carbon atoms. That's why secondary it is coming. Now if you analyze this one, you could understand this hydrogen is coming here. So all 4 valencies are different, correct? So you have CH3 here and ethyl group here, chlorine here, hydrogen here, all are different. So I can say this carbon is chiral. So what is the answer for this question? Answer for this question is secondary butyl chloride. Clear? Now we will go to the next question. Go through this question. Which of the following molecule has chiral carbon? So please again the same rule. If it's a central carbon, 1 carbon system. Okay, if you see here all these are 1 carbon system. Focus is on this carbon. Okay. Now if 4 valencies are different, we say that carbon atom is chiral. Now if you look here, here chlorine, okay, here hydrogen, that's fine, here methyl, and here also it is methyl. Another way of representation of CH3 is Me, correct? So these 2 are identical. So we can say that this is a chiral. This carbon center is a chiral, not chiral. Now if you look at here, we can see here OH is present. Here H is present, okay, but here C2H5 and here also C2H5. So this is also a chiral, correct? Now we are looking at the option C. In option C, if you see here ethyl and here methyl, but here both are hydrogen atoms. So we can say this is also a chiral in nature. Now let us look at option D. In option D, we can see bromine, fluorine, iodine, chlorine. All 4 valencies are different. So we can say this is chiral carbon. This is a chiral carbon. So answer is option D is the correct answer. Clear? Can we go to next question? Okay, so I hope you could see the new question here. Just go through the question. How many chiral carbon atoms are present in the below molecule? So you could see the molecule here, okay, and the options you can see 1, 2, 3, 4. So how will you check it whether how many chiral carbon atoms are there? The first carbon I am checking, I could understand. I will expand it and draw. So you have hydrogen here, okay, here also hydrogen, and here also hydrogen. So since three valencies are same, I can say that this is not chiral. Correct? So this carbon is not chiral. Now I am looking at the next carbon. So if in this carbon I could see one valency is hydrogen. Okay, one valency is hydrogen, other valency is chlorine, and the third valency is methyl group connected like this, and the fourth valency is this big group that is connected here. So I can say all four valencies are here different. So I can say this carbon is chiral in nature. This is chiral. Correct? Now let's look at the next carbon. Now I am going to the other one. When I am going to the other one, I will rub all these things. Otherwise you will get into confusion. Okay? So that is very important. You should rub the existing one and analyze it. Okay. Now let's say we'll go to the other carbon and see whether it is chiral or not. Okay. Now when I am looking at this carbon, you could see here hydrogen. So I am expanding it and draw hydrogen here. So one valency is this one, this big group. Other valency is hydrogen, and the third valency is ethyl group, and the fourth valency is this isopropyl group. So this is also chiral in nature. So I can say this carbon is also chiral. Now if you look at this carbon C2H5, we know that two hydrogen atoms are already there, CH2, CH3, so it won't be chiral. Here also if you see this carbon atom, you have one CH3 here, one CH3 here, so both are identical. So as such I can say there are two chiral carbon atoms, one is this one and other is this one. So the answer is option B. I hope it is clear for you. Please try it out. Now we'll go to the next theory part. Okay, we need to understand how to calculate the number of stereoisomers. That is what we are going to do next. Okay. So next we will do the calculation of number of stereoisomers. So we know we will have different workouts actually. So we have different classes of compounds. So the first class of compound that comes under this category is compounds having dissimilar end. Dissimilar ends. So dissimilar means if you see here this compound, if you see here one end is C2H5, okay, the other end is CH3, okay, and you can see this is a chiral carbon. One is hydrogen atom, okay, you can see here one is hydrogen atom, other is OH, other is C2H5, and other is a big group. And if you look at this carbon atom also, you can see one is hydrogen atom, other is OH, one is CH3, and other is a big group. So I can say both of these are chiral carbon atoms. Okay, and this like compound having dissimilar end. This end is different from this end. Correct? Okay, in this case, if the compound is like this, then how will you calculate the number of optically active isomers? The number of optically active isomers will be equal to 2 raised to n. Here n indicates what? N is the number of chiral centers. So in this case you can see this is one center, this is another center. So the number of chiral centers in this example is 2. So I can say here the answer is 2 power 2, that is equal to 4. And next one is number of meso compounds for this one. So we know that there is no plane, no imaginary plane which can separate this into two equal halves. Then only we call that as a meso compound. A meso compound is a compound having minimum 2 chiral centers and there is a mandatory plane of symmetry. But here there is no plane of symmetry possible. So that's why they say number of meso compounds is equal to 0 because dissimilar ends are there. And total number of stereoisomers is equal to number of optically active isomers plus number of meso compounds. So here we know 2 power n plus 0, that is 2 power n. So in this case the answer is here, this answer is also 4. Check whether you have understood or not. I hope it is clear for you. Next we will try to learn compounds having dissimilar ends we have learned. Next we are going to learn compounds having similar end. Okay. Next I am going to explain the second case here, that is compounds. Okay, compounds having similar ends. You can see here similar ends. Here also CH3. Similar ends with the even number of chiral centers. Then you can ask me one doubt here. Sir, why can't be with dissimilar ends even and odd number? It is possible. But whenever it is dissimilar, always the number of meso compounds is 0. So there is no point in discussing with even number of chiral carbon atoms and odd number. That is the reason only when similar ends are coming, then you will have separate formulas whenever there are even chiral centers and when there are odd number of chiral centers. So first one I am going to explain here is compounds having similar ends with even chiral centers. Okay, so we will see the compound. Here you can see CH3, both ends are similar, CH3, and here also CH3, and we can see this one, this is a different group, this is a different group, this is a different group, and this is a big different group. So I can say this is chiral. Here also one is CH3, one is OH, one is hydrogen, and this is another big group. So this is also chiral in nature. But we can understand that since both ends are similar and you have two chiral carbon, but if you draw a plane through the center, we can see here both halves are similar. That means there can be the possibility of existence of meso compound. So in this case, the number of optically active isomers is equal to 2 power n minus 1. Okay, 2 power n minus 1. So in number of meso compounds will be equal to 2 power n by 2, 2 power n by 2 minus 1. And the total number of stereoisomers will be the sum of these two. So 2 power n minus 1 plus 2 power n by 2 minus 1. Now let us calculate for this example the number of optically active isomers. So we know that here number of chiral carbon atoms is equal to 2. So let us substitute here. So on substituting, this will become 2 power 2 minus 1. That is 2 minus 1 is 1. So the answer here is 2. Clear? Now let us calculate the number of meso compounds. So 2 power n by 2. So n is 2. So 2 by 2 minus 1. So that is what actually 2 power 1 minus 1. So 1 minus 1, 0. So answer is 1. So we know that there is one meso compound possible. One plane is there. Now total number of stereoisomers will be the sum of these and this. So I can say that is 2 plus 1, which is equal to 3. 3 will be the correct answer. I hope you understood. Clear? Next we will discuss compounds having similar ends with the odd number of chiral centers. Okay, so next we are going to discuss compounds having similar ends with the odd chiral centers. So here if you can see similar ends, CH3 is here, here also CH3. But if you look at the number of chiral centers, you can see here this carbon, one is CH3, one is OH, one is H, and other is a big group. So this is a chiral center. This one if you see, this is C, you can see here, this is connected to CHOH, CH3, this is connected to CHOH, CH3, this is OH, and this is also hydrogen. So this is also chiral center. And this is also chiral center. Correct? Now here when you look at this carbon atom, which is lying between these two chiral centers, you may feel like this is achiral because this is CHOH, CH3, and this is CHOH, CH3. But actually speaking, this is also chiral. Whenever it comes between two other chiral centers, this carbon is called a prochiral carbon. With one change, this will become chiral. So that will be considered as chiral, and with that we will calculate it. Okay. Now let's see the number of optically active isomers. The formula here is 2 power n minus 1 minus 2 power n minus 1 by 2. So here n value we can say 2, n is how much? 3. So 2 power 3 minus 1 minus 2 power 3 minus 1 by 2. 3 minus 1 is 2 by 2. So how much it will become? We can say this becomes 2 power 2 minus 2 power 1. That is 4 minus 2. You will get the answer as 2 here. So the number of optically active isomers in this case is equal to 2. So I can rub this. So you will get the answer for number of optically active isomers is equal to 2. Okay. Now number of meso compounds here is equal to 2 power n minus 1 by 2. So that is 2 power n is 3. 3 minus 1 divided by 2. That is 2 by 2 again. So you will 2 raised to 1 and you will get it as 2. Correct? Now next one, total number of stereoisomers. Total number of stereoisomers is the sum of this and this. So I should get 4. We can directly put it in the formula. You can say n is equal to 3 here. So you can substitute directly here. So 2 power 3 minus 1. So that is equal to 2 power 2, that is equal to 4. You are getting the same thing. And please remember, in exam paper they will ask you calculate the total number of stereoisomers, or they may ask you calculate the total number of optical isomers. Both are same. This is different. This is optically active isomers. Clear? So don't confuse it. Whenever in exam they are asking you calculate the total number of optical isomers, don't calculate number of optically active isomers. That is wrong. So whenever they are asking calculate the total number of optical isomers or stereoisomers, you need to calculate both optically active isomers and meso compounds and add it. This is one method. Or you can use the formula that is given here directly. Both will give you the same answer. Clear? So I hope almost all the three possibilities we have discussed. Now let's go to some of the important question discussion. Okay, I hope this is clear for you. This is very important. In exam paper, most of the time they are asking you to calculate the number of optical isomers. It means the total number of stereoisomers only. Okay, don't get confused with optically active isomers. That is different. Okay. Okay. So now let us discuss some of the special points associated with optical isomerism. See here. One such special point comes with biphenyls. This type of compounds where two benzene rings are linked together, they are called biphenyls. Now if you observe these biphenyls, you can see there is no chiral carbon atoms are here, because if you see here or look at here, there is no chiral carbon atoms are not present here, but this compound is optically active because you have double bond. Okay, I remove this and will put this one, then it becomes more clear. So if there is double bond is there, that means two valencies are associated with the same thing. So I can say there is no chiral carbon atoms present here. Okay. Now, but this compound is still optically active. The reason for that is, we can say always ortho substituted. What is the ortho position with here? This is one ortho, this is another ortho. Here also this is ortho, this is ortho. Ortho substituted biphenyls are optically active. This you need to remember. This is a fact. The reason for that is, here one of the biphenyl is in horizontal plane. That's why I have shown in black color here. This is in horizontal plane and this is in vertical plane. And since both of them are in different plane, it will show optical isomerism. Okay. And other important thing to remember here is they should be ortho substituted, and this both ortho position should be differently. The substitution should be different. Here also NO2 and here also NO2. Then it is not possible. Both ortho substitution should be different. Here also COH and here NO2. So both are different. In that case, it will exhibit optical isomerism. I hope it is clear for you. Now similarly, other such type of compound is substituted allenes. If you see here allenes, we can see again double bond. That means two valencies are same, but they are on seeing this we may feel they don't have any chiral carbon atom, but they are optically active. But very important condition, always count the number of double bonds. This number of double bonds should be even. It should not be odd. If they are even, then only they will exhibit optical isomerism. And other important condition is the sp2 hybridized carbon, that is the terminal carbon, this should be substituted and they should be different. X should not be equal to Y. If X is equal to Y, then also this will not exhibit what? Optical isomerism. So two conditions, it should have even number of double bonds, and the second condition is the carbon atom, the sp2 hybridized both terminal carbon atoms should be substituted differently. Then only we say substituted allenes, they are optically active. I hope these 2 points are clear for you. Yes. Now we'll go to the third and fourth special point. Okay. So next to discuss the third special point here is, so first two special point was, we were telling there was no chiral carbon atoms and the compounds were exhibiting optical activity. Now I am going to say about those compounds which have chiral carbon atoms, but still it will not show optical activity. Let's see here one example. So in this case, first case, chiral nitrogen which is present in a 3-degree amine, okay, does not show optical isomerism. So if you see a 3-degree amine, we know one is lone pair, other is R1, this is R2 and R3, and we know that here let us assume R1 not equal to R2 not equal to R3. But this compound will not show optical isomerism. The reason for that is this can be interconverted. You can see here R3 is coming here, R2 is coming here, R1 is coming here. So that is, it is interconvertible. So what is the problem when it is interconvertible? That is at room temperature. So when it is interconvertible, the problem here is we will be taking this molecule and passing the PPL, and for example we will get, for example, dextrorotatory, and we are taking the same compound at some other time and passing PPL, but at room temperature this can change to this form and it will rotate the plane of polarized light in other way. So we cannot say this is optically active. Optically active means that will rotate the PPL towards one direction all the time. Okay, so this is one special case you should remember. Then the other one is chiral carbon, which is present in carbanion. So if you see carbanion, it has the same structure, but only difference is carbon is present and you have a negative charge. And this chiral carbon which is present in carbanion also will not show optical isomerism. Even though we say here R1 is not equal to R2, not equal to R3. So we may feel all four are different valencies, but again the reason is same. This is also interconvertible. At room temperature. Clear? Very, very important. So please remember 3-degree amines having different alkyl groups will not show optical activity, and carbanion with a negative charge and having 3 different alkyl groups also will not show optical activity. Clear? I hope this is clear for you. Now we will go to questions. Okay, so we have a new question in front of you. Which of the following is optically active? That is the question. Okay, so if you see here, the first one, we know that 4 valencies should be different. That's how we consider a compound as optically active. Now if you look at this carbon, we know that there are 2 valencies going like this, so other 2 should be hydrogen atom. If 2 atoms are similar, then we say it is not optically active. Here also we say this carbon, 2 valencies going like this, and we have other 2 valencies are hydrogen atom. So we can say this is also not optically active. And now we are looking at this carbon, so 2 valencies are going like this, that is to carbon and some other thing, but here you have one more valency left, that is hydrogen atom, so that is also not optically active. Now looking at the next one, you can see here one valency is CH3, one valency is chlorine, and other 2 valencies are connected to a ring. But we know that this ring is symmetrical. If I find a plane like this, you can see the upper half is similar to the lower half. 1, 2, 3, here also 1, 2, 3. Upper half is similar to the lower half. In that case, we cannot say this as a chiral carbon. So all the carbon atoms present here are not chiral. Now looking at the next one, you can see whenever 2 valencies are there in a carbon atom, the other 2 should be hydrogen atom. Okay, here also hydrogen atom, here also hydrogen atom, here 1 is hydrogen, so other should be hydrogen atom. This is also hydrogen atom, and here also 2 hydrogen atom. Now we can see here in all the carbon atoms there are 2 hydrogen atoms are present, so that means 2 similar atoms are present. So none of the carbon atoms present here are not chiral. Now let us look at the third option, C. Now looking at third option, we could understand this carbon atom, it has 2 hydrogen atom, so not possible. Here we know that 1 valency goes like this, other 2 valencies are going like this, there is only 1 hydrogen atom here. Okay, and we know that chiral carbon atoms are applicable only for sp3 hybridized carbon. This is sp2 hybridized, so here not applicable. This is also sp2 hybridized, not applicable. Now comes to here. Here if you come, you can see one is CH3, other is chlorine, and the other is a ring like that. Next 2 valencies are going to a ring, and if you are trying to find a symmetry in the ring, we could understand the upper half is not similar to the lower half. We cannot find any symmetry with respect to this carbon atom. So that means this carbon is chiral in nature. This is chiral. So the answer should be option C. Now let's look at option D. Okay, so in option D, if you are seeing here also the valency nothing is there, so this should be hydrogen atom. Here also this should be hydrogen atom. Okay, here also this should be hydrogen atom. Not, and this is sp2. Okay, and this is also sp2. Now looking at this one, you can understand one is methyl. Nothing is mentioned here. If nothing is mentioned, this is also methyl. Since both are similar, this cannot also be chiral carbon. So the answer here is option C. I hope you understood clearly. Now let's go to the next question. So we have a new question in front of you. Just go through the question. Which of the following is not optically active? So what is given here is substituted allenes, right? So we know in the case of allenes, 2 points to be checked. First is check the number of double bonds. The number of double bonds should be even in number. Next thing is check the sp2 hybridized carbon atom, that should be substituted differently. Now first we are looking here, this is my there are even number of double bonds are there. Here when I am looking at this carbon atom, I could understand there is one hydrogen atom present here and one CH3. Here also one hydrogen atom and one CH3. Both are substituted differently. Here CH3 and H is not equal, CH3 and H is not equal. So this is, we can say this is optically active in nature. This compound is optically active, OA. Question is not optically active. Let's go to next question. If you see the next question, you can see very clearly number of double bonds are even, but you can see here CH2. So that means here also hydrogen, here also hydrogen. So that means sp2 hybridized carbon atom, it is not differently substituted. Both are same. So I can say this will not exhibit optical activity. So the answer should be option B. Now let's go to option C. You can see even number of double bonds and both are differently substituted. So this is also optically active. Okay, this is also optically active. Now we'll go to the last one. Here also we can see even number of double bonds, and here it is methyl, here it is ethyl, here it is chlorine, and here it is bromine. Different, they are substituted differently. So the answer should be which one? The answer should be option B should be the correct answer. Clear? I hope it is clear for you. Now we will switch to the next question. Okay. We have a new question in front of you. I hope all of you could see it. Question here is, which of the following has S configuration? So we need to identify. The first one given here is a Fisher projection formula. Okay. So I have already taught you how to do that. So first thing what we need to do, we need to assign priority. So on assigning priority, we could understand F comes first actually, atomic number highest. So we will give 1 to this one. Then you have CH3, both are carbon atoms and other is hydrogen. But here CH3 means all the connected groups are hydrogen. But here the connected group means carbon and 2 hydrogen, because this CH2 is one connected to carbon and other 2 hydrogen. So carbon comes first. So this will be second priority and this will be third one and this is fourth priority. Now we understood that the fourth priority or the least priority group is on vertical line. So with respect to vertical line, we have the formula VCR, correct? And other thing is vertical anti-clockwise, then it is S. Vertical clockwise R, vertical anti-clockwise S. This you need to remember. Now we see the rotation. So 1 to 2, see the rotation from 1 to 2 and 2 to 3. So in what direction it is rotating? It is rotating clockwise. So I can say least priority group is present in vertical side and the rotation is clockwise. So its configuration is actually what? I can say its configuration is R. But in the question they are asking which of the following has S configuration. Now let's look at the other one. So if you see here in this one, again I am assigning the priority 1, then CH3 and CH2, this will have its second priority and this is having third priority and this is having fourth of priority. But we know that in this projection, wedge dash projection, always the least priority group should be present in away form, like dash form. So we need to interchange this. So let's say I will draw like this. This is 1. Okay. I am going to interchange this one. So here 3 will come. Okay. And here 4 will come. Correct. And here 2 will come. Now find the rotation from 1 to 2 and 2 to 3. 1 to 2, 2 to 3. Some students ask, sir, why we are not doing 1 to 2 like this? Because we are going from 2 to 3. Then we cannot go again like this. That is not possible. That's why 1, 2, 3. Now in what direction it is rotating? You can see this is rotating in anti-clockwise. So anti-clockwise means it is S configuration. But we have done one change. So we need to take opposite of this one. So the actual configuration here is R. So this one is R configuration. Now next look at the option C. So here also we need to assign priority. So this one is 1 and this one is 2, this one is 3 and this one is 4. Now we again understood that the least priority group is not present along with the dash. So we need to interchange between 4 and 3. So let me draw again. So this is 1, okay, this is 2, okay. Now I am going to interchange this one. So this becomes 3 and this becomes 4. Now go from 1 to 2, then 2 to 3. So see how it is rotating. It is clockwise rotation. It is clockwise. If it is clockwise, we know Roman Catholics, so this will be R. But we know that we had done one change between 3 and 4. So the actual configuration should be opposite of this one, that is S. So this is actually S configuration. Now let's see the last one. So in the last one you can see here again this is on Fisher projection formula. So we assign the priority 1 and this is 2 and this is 3 and this is 4. Now let's go from 1 to 2, then 2 to 3. So in what direction it is rotating? It is rotating in anti-clockwise direction and the least priority is present on horizontal side. So on horizontal side we know HAR, HAR, correct? So please see here, horizontal, least priority group is on horizontal and it is rotating anti-clockwise, so its configuration should be R. Yesterday I have taught you this technique. So I could understand this is R, this is also R. We have seen this is also R and this is the only one which is S and this is R. This is also R. So the answer should be option C should be the correct answer. I hope it is clear for you. If you have any doubt, feel free to ask. Okay. Okay, so we have a new question in front of you. The absolute configuration of the compound is. This is very important question as well. Now here they have not given a compound with one chiral center, two chiral center. If you see here, this is a chiral center because CH3, HCl and a big group. And this is also a chiral center, H, C2H5, Cl and another CH, big group. So two chiral centers. So first thing, they have given the option as 2s3r, 2s3s. They want to identify whether this is S or R and this as S or R. But before that, we need to know which is 2 and 3 here. How you can do that? First of all, please draw this compound separately. CH3, this is CHCl, okay, and you have one more CHCl. Okay, CHCl, then you have CH2, CH3. This is the compound. Please see that. Now next step is numbering the compound. On numbering, we could understand this is the longest possible chain. Okay, and if you are numbering 1, 2, 3, like this only we can number it. If you go from here, 3 is the number is coming here and 4 will come, and that is the biggest locant. Here if you go, you will get 2, 3 as the locant. So I can say from here the numbering happens. So this is carbon number 2 and this is carbon number 3. Please do that. Please identify that. This is not prioritizing. This is identifying the carbon as 2 and 3. So I will mark it with a very different color for you. So this is carbon number 2. This is carbon number 2 for you. And this is carbon number 3 for you. Okay. Once this is identified, you can rub this one. There is no need further. Okay. Now next step is identifying the configuration of this second carbon. So how will you do that? Again the same concept. We will give priorities. So chlorine, this is connected to chlorine, carbon, hydrogen and carbon. So highest one is chlorine. Now next one is, this is carbon and this is also carbon. But this carbon has its nearby locants as chlorine, then another carbon and hydrogen. But this carbon, if you see, the locants are hydrogen, comma, hydrogen, comma, hydrogen. So if you compare, chlorine has the highest priority. So I may say this is priority number second carbon, second priority. And we know this is third and this is fourth one. So this I am finding out with respect to this one. Now move from 1 to 2 and 2 to 3. So we could understand in what way it is rotating, anti-clockwise. So we understood least priority group is in horizontal. So we say H and it is rotating anti-clockwise, HA. We know that HA means it is HAR. So the system should be what actually? This 2 should be, this carbon should be R. So I understood 2R. So 2R is present in 2 options. Now let's go to the next one and assign the priority. So we will rub all these things. Okay. So that is very important. Otherwise you may get confused. So we will rub all the things that we have given. Okay. So assigning all priority, everything we will rub it. Very, very important. Otherwise you may end up with the wrong answer. Okay. Now we will start numbering for the third carbon in the same way. Now see here, while assigning priority for this one, again we know chlorine has the highest priority 1. Then we have carbon here and here also carbon. But here in this case carbon is connected to chlorine. But here CH2, CH3, so 2 carbon atoms. So second priority for this one. Then third one this one and fourth one this one. Now move from 1 to 2, 1 to 2. Okay, then 2 to 3. So I could understand it is moving in the clockwise direction. Clockwise direction. Now and horizontal system. We know that HAR. Horizontal anti-clockwise means R. Now horizontal, this is in what direction? Clockwise. Clockwise means opposite of this one, that is S. So I could understand this is S configuration. So now tell me what is the answer? 2R. Second carbon is R and third carbon is S. Third carbon is S. So option C should be the correct answer. Clear? All of you? Okay, so we have the new question in front of you. Just go through the question. Which of the following is optically active? Now we know that if you look at the option A, we can see here chiral carbon with OH is present, hydrogen, COOH and a big group. But here also OH, H, COOH and a big group. But we know that this is also a meso compound. We know that meso compounds are optically what? Why we say meso compound? You have 2 chiral carbon, but there is a plane which separates this compound into 2 equal halves. So that means this compound is optically inactive. Why? Because if this is rotating this compound through maybe say 50 degree in this direction, then this half will rotate the same compound in minus 50 degree. So this type of compensation we have learned it, that is called internal compensation. As a result, there is no optical rotation for the plane polarized light. So we say meso compounds are optically inactive due to internal compensation. Now next one, option B, if you see, we can see here both are hydrogen atom, so not optically active carbon, not a chiral carbon. Here also both hydrogen atom and here also both are hydrogen atom, and here also we can see one is methyl and other is free. That means it is also methyl. So that is also not optically active. Now let's look at the option C. So if C, you can see here hydrogen atom, other is chlorine atom, other is ethyl group and other is methyl group. All 4 valencies are different. So I can say this is optically active. C option is the correct. And option D, if you see, this is OH group, this is hydrogen and this is COOH and this is also OH. But they have just shown the bond between oxygen and hydrogen. So these 2 are similar. So I can say this is also optically inactive. So the optically active compound is option C alone. Clear? I hope it is clear for you. Okay.